All right, welcome everybody. Thanks for coming today. This webinar is going to be on the magic of multilingual search. And I'm really excited to help everybody learn about using and applying multilingual search to whatever you might be working on. This is me. I'm Arjun. I'm a developer advocate at Pinecone, and I love making technical content and blog posts and all that good stuff. And the thing I love the most is learning about something that's really interesting or challenging and making it more digestible for other people to use and think about. And recently, I've been thinking really hard about what multilingual search is, how it works, how we can use it, so on and so forth. Because I think that it's very easy to take it as a given, much like how we take universal translation as a given. But there's a lot to unpack there. And I hope that during this webinar, we can kind of uncover how this works, how we can apply it for vector search, so on and so forth. And just so everybody knows, we'll be recording the talk, so you can rewatch this much later. And there's an open Q&A. So if you have any questions during the talk, we have set aside about 20 minutes at the end of this in order to answer those. So please throw them in there as you get them. What we'll be going over today is why we need multilingual search, specifically multilingual semantic search. We're going to have a mini crash course going from very little knowledge about what search and vectors are and so on and so forth, and ending at what multilingual semantic search is and how you can use it. We're going to learn a bit about vector embeddings. We're going to learn about how multilingual large language models are made and why they're able to represent concepts across languages. We'll learn about how to take a multilingual large language model and turn it into an embedding model that's great for multilingual semantic search through the lens of multilingual E5 large and Pinecone Serverless and Inference. And finally, I'll show you a demo that applies cross-lingual and monolingual search to a language learning problem. So not only will you learn about these things, but you'll also see how to use them in a semantic search application. All right, having said that, let's dive right in. So let's say you wanted to learn Spanish because you're an English speaker and you're trying to pick up a second language. Your class assignment is to write about your weekend trip that you took to a local park. There's this website called Tatoeba that you come across, which is basically a really good search engine for sentence translations. Contributors can go on the website, type in a sentence, and if you speak another language, you can type in the translation of that sentence in order to help other learners find sentence translations. And the nice property here is that if there are enough pairs across languages, you can start to connect things across those languages and learn about how people say things in all sorts of ways. And your teacher is kind of tasked you to use this website to help you create your response. But there's one big problem. The problem is that Tatoeba only supports keyword search, which means if you search for a word like park, you're going to get sentences that are related to parking, which is completely different than going to a park. So there's an overloading on the keywords here. What would really be nice, and of course, if you look for exact sentence translations, if you look for exact English sentences and look for Spanish sentences back, you're just going to get exact translations of that sentence in different variations, which might not be as interesting to you if you're trying to write a paragraph or an essay about what you did. You might want lots of variation in what you're doing. It would be really great if instead of typing in a concept or a set of words and getting back just the keyword overlap of all the sentences that are on the website, we would actually find not only the literal sentence translation that could exist on the website, but any similar and relevant sentences that are along the lines of whatever concept we're interested in, which is going to a park for a weekend trip, in addition to that translation. Keyword search can't help us do that because it's not easy to abstract that concept out using just the words that are there. This is a multilingual semantic search problem. We're trying to search over a corpus that exists in multiple languages, using multiple languages, and we're specifically looking for a comparison with respect to meaning rather than keyword overlap. Now, when we talk about multilingual semantic search, we're not only talking about cross-lingual search, which is not as common of an application, but we're also talking about scaling semantic search across languages. So if you have a bunch of customers that speak in English and need to access English documents, you can reuse the same pipeline for customers who speak Spanish and are trying to search for Spanish documents. That's a benefit of doing multilingual semantic search in the way that we're going to show today. And of course, offering that cross-lingual approach could be useful in certain specific applications. For example, if you're trying to analyze reviews and you have reviews coming in from loads of countries all over the world, you might want to do some sort of topical analysis on those reviews or cluster them in vector space. Multilingual semantic search can help you do that. If you want to make your documentation more accessible to people who speak English as a second language, you could enable multilingual semantic search to not only help English speakers figure out what they need, but also to help anybody typing in any language to find the documentation that you're interested in. Also, the application that we're going to be interested in is going to be education, which is helping people figure out how to find these relevant sentences. The other things that you can do is just scale your existing multilingual semantic search pipelines, which is what I've said prior, or you can learn about companies around the world if you're in some sort of financial domain by enabling this type of semantic search. So that's all well and good, but how do we actually achieve and build this type of multilingual semantic search system? It sounds very complicated, like how can we translate all these languages or create these concepts across them and actually index the information? So we break the problem down into two parts. The first is we need a way to represent information across languages. And the second is we need a way to efficiently search over this information, especially as the corpus scales. So we're going to solve the first problem by understanding multilingual embedding large language models. And we'll solve the second problem by using Pinecone and Pinecone's vector database. Now, before we go into that, it's really important to kind of level set on what we know about how large language models work and how we can use large language models to get embeddings. In the AI space, there are lots of vocabulary, lots of words that are kind of thrown around. It can get very intimidating to kind of wade through all of that in order to build the thing that you're actually interested in building. And at the end of this talk, I hope to kind of defog all of the confusion that can exist around these terms and to give you a nice way of kind of thinking about what you need to know in order to start building such a system. And it turns out it's not actually that much. So we're going to start right at the beginning. What are vectors and what are vector embeddings? As a refresher, vectors, I like to think about them as ways of representing non-mathematical objects into fixed size lists of numbers. So you can see on my diagram on the right, we have a sentence, which is I went to the park over the weekend. We toss it at a vector embedding model, whatever that may be, and it outputs this fixed size list of numbers, usually floating point numbers. And usually it's fixed size because we want to compress information into the same dimension for reasons that are important later. Now, the nice thing about turning non-mathematical things into mathematical things is that you can apply mathematical rules to those things. For example, if you have a list of numbers and you map that to a coordinate space, there are certain properties about those vectors that exist in coordinate space that you can do comparison on in order to understand their relationship to one another. So it would be super cool if we had a magic box that could take us from whatever sentence we're interested in. For example, a question like when were the Normans in Normandy? And help us cluster that representation close to responses that would be relevant. For example, this longer context that explains when and where the Normans were in Normandy. So that's nice because if we can measure similarness in content and relevance with respect to where these concepts exist in vector space, then we can automate the process of searching for things that are similar without having to worry about thinking of ways of handling what these concepts are and what words people are using, what they're trying to communicate. If we can just directly transform those things into the mathematical space we're interested in, we don't have to think about how we have to do additional pre-processing to get that information out. We can just take the representation as it is and its transformation into whatever space we're looking at. We're getting a little ahead of ourselves because I haven't necessarily justified why this is possible for text in the first place. When I try to explain to people what vector embeddings are, I really like to start from the distributional hypothesis, which is this idea from computational linguistics. Basically, the theory goes that if you have a bunch of words in a giant corpus, think of all the literature in the world or all of the Wikipedia articles on Wikipedia. If you were to look at words, specific single words or sets of words like bigrams or trigrams or what have you, how they cluster in vector space should be relative to how they are co-occurring inside those texts. So if you think about the word moon and the word space, you expect to see those words closer to one another inside text than you would relative to other unrelated words like oceans or fish or something like that. So there's something interesting about this property of co-occurrence that happens in language that we should be able to take advantage of in order to learn text representations of those words. For example, maybe there's something we can learn about the word space by looking at the words that surround the word space in the wild. That's the basic idea. And so when we think about how we're learning these models for language, we are really thinking about some heuristic or some way of understanding how these words, sentences, documents are distributed across the text that we're working with. Hence, language models, right? Modeling language models, because we're trying to understand this property. I want you to keep in mind co-occurrence and this idea of words and concepts co-occurring together as we progress through the rest of this webinar, but that kind of helps me develop a more theoretical understanding of what's kind of going on. Okay, so LLMs, like what are they, or what do you need to know? I think the most important thing to take away here is going to be that large language models are basically extremely powerful neural networks that have been trained on billions of text data points, which have learned this ability to abstract concept and meaning from different sentences based on certain properties of that text corpus. And what large language models allow us to do is take arbitrary words, documents, sentences, and turn them into vector embeddings in such a manner that they encode the meaning of contained inside those words, sentences, or documents in those vector embeddings, such that we can do computation on those vector embeddings to compare the meaning, the relevance, or whatever other properties we're interested in the content of the text for the type of applications that we're building. That's why large language models are super useful for us. So the first large language model we're going to talk about is XLM-RoBERTA, because it was the first biggest example of scaling up training of this type of unsupervised co-occurrence LLM approach for creating a really good multilingual embedding model. So a lot of the models that were multilingual trained before this point in about 2020 they were pretty large, but they weren't trained at the entire internet's worth of scale. And basically the contribution of this paper is that if you scale up this effort and you have some clever ways of handling all the different types of languages that exist in the world, you can actually build a really good multilingual, cross-lingual embedding representation of the languages inside this corpus just by working on this scaling up. The key contributions and the key innovations that occur from this paper that allow us to create this representation across languages are going to be this training data scale-up, language agnostic tokenization, and this training objective of masked language modeling in order to get multilingual embeddings. And we're going to go over what each of these are really quickly just to get us a good understanding of why this model works as well as it does. The dataset that XLM-RoBERTA uses is massive. It covers 88 different languages. You can see that this is a graph from the paper, and on the y-axis is powers of 10, so it's a log scale in gigabytes. And basically, the XLM-RoBERTA paper is using both halves of the dataset that are being described here. Common Crawl, which is basically a huge portion, if not all, of the internet, and Wikipedia. And the x-axis here is going to be all of the languages that are within the corpus. One thing I want you to keep in mind is that a lot of the approach before this paper was kind of trying to create models for specific languages or trying to indicate when a specific language was in use or inside the corpus. And this paper kind of does away with that. There's no indication of like what language is being trained on at any given point, and there's no separation in the tokenization of those languages. And that's actually kind of nice because languages exist in families. And so if you have low resource languages like the ones that exist at the right side of this graph, which might not have as much data as the ones in English or Russian or all these other languages, you can leverage the fact that these languages have similar behavior to one another in order to get enough data that you need to represent what that language is doing. And that's why training across languages can be really beneficial. Of course, with this specific paper, there is a little bit of an asterisk on that. There is a limit on how well this works as you scale up, but with subsequent papers, we've kind of seen this work pretty good to scale across languages. So, okay, so the next biggest problem is the one that I find really interesting as a former data scientist, was how are they able to handle like all of these different languages? Languages use loads of different characters, loads of different concepts, they might be written differently, so on and so forth. How are they able to stuff this into the model that's being applied? So what they did was they were able to use a tokenizer in order to break up all of these words that exist across these languages into subwords, which are called tokens. So you can see on the right side of the screen, we have this application where you can pass in a sentence. It breaks the sentence up into how we view it, which is by words. And when we pass it to the tokenizer, which is this magical box, it splits up these things into subwords and then assigns them IDs based on how on the unique subword that they correlate to. Now, this is important because if we took every single vocab word from all the 88 languages, that would be way too many representations for our model to learn. Rather, we want to create a smaller set of subwords that covers as much of the variation in languages as possible, and then contextually learn embeddings on those subwords in order to address all of them. And the XLM-R paper uses 250K token vocabulary in order to cover all of those languages. And just like how I said prior that some languages exist in language families, so there is a little bit of overlap, that's kind of where the tokenizer is able to kind of handle those different things. And this is not intuitive, or this is not straightforward to handle across languages, but they were able to kind of address this in order to learn these token representations at scale across them. Second is the learning objective. The big learning objective that XLM-RoBERTA uses is masked language modeling. What this means is that the way we're trying to understand the representations of the concepts that we're working on is going to be based on this idea of co-occurrence inside sentence text. So we might have some sentence like, I want to play in the park. We apply a mask to the sentence, which basically just randomly drops out portions of the words that exist in the sentence. And then we ask the large language model, can you predict the words that should have been here? Just like the idea that I was explaining earlier about the distributional hypothesis and word co-occurrence, maybe there's something useful we can learn about what these words mean in context based on the words that they are surrounded by. And maybe by teaching a large language model to predict the missing words, we can have it learn really good intermediate representations of what those words are going to mean or do. And that's what ends up happening with large language models. Now, for the astute among you, you might realize that this type of model is only going to learn token level embeddings, which is this idea that you have these subwords and you're learning representations for those subwords, but it's not necessarily intuitive how we go from token level embeddings to document level embeddings, like when we have larger queries or things like that. What XLM-RoBERTA does is it actually uses mean pooling. So it averages all the token vectors in order to get some representation, but we'll see that that isn't actually good enough for our purposes. What do I mean by that? Why isn't that good enough for our purposes? Well, it turns out that XLM-RoBERTA is really powerful at representing tokens, really powerful at representing concepts, but it's not that great at producing document level embeddings. It doesn't even produce those directly. You have to apply some transformation in order to get that. What we really want for a good vector search application is an embedding that can handle asymmetries in search. It's the idea that you might have queries, which could be really short or really long, questions or queries that people are passing to a search engine, and then you'll have documents, which could be longer chunks of information that might represent concepts differently than the queries will. We also want some sort of vector embedding that can help us deal with relevance and importance in search, in addition to multilingualism and semantic information, which XLM-RoBERTA might not be so great at because it wasn't trained with these objectives in mind. So what do we do if we want that? Well, this is where the multilingual E5 large model comes in. The cool thing about the multilingual E5 large model, which the technical report for it was released earlier this year, is that it's actually based on the XLM-R-RoBERTA model. So it gets a lot of its multilingualism from there. But the researchers apply the same three concepts of having really great training data, a solid training process, and a fine-tuning mechanism in order to create fantastic document level embeddings for a search within and across languages. And we're going to kind of talk about how multilingual E5 large is able to achieve this. So the biggest reason why multilingual E5 large is able to kind of address this in the first place is at the dataset level. When we were working with data in the previous task with XLM-R-RoBERTA, we were kind of looking at a synthetic data task, right? Where we have some text, we're applying some modification to that text, and we're learning about properties of that text relative to the modification that we're making. The researchers in this paper were like, well, that works really well and you can scale up that approach, but we're kind of hitting the limits of how well we can learn these search embeddings based on that synthetic approach. And then on the other hand, you have manually human labeled data. You might have people who have done queries on some search engine, find the relevant results and labeled them, but this is extremely expensive to get. So even though that data is really high quality and we need a lot more of that, that's also really hard to scale up. So what can we change about the training data used for these search models in order to kind of get them to work a lot better in the context that we're interested in? So the researchers set out to scrape a bunch of real world text pairs, i.e. pairs of text that occur close together in text vector space in order to take advantage of the fact that if these texts do occur close together in vector space, that probably, or in text space, that probably encodes some sort of relevance information. So here are a few categories of the data that they used. They used article and content data from places like Wikipedia, but also on the internet. For example, you might have a title that's just one word or a couple words like origami, and you'll have a little passage that kind of corresponds to its relationship to that title. You might have translation pairs that might exist on the internet, like on Tatoeba. You might have question answering that exists in different languages, and the question and the answer are going to be relevant to one another, especially if the answer is correct relative to the question. Taking advantage of these natural pairs that exist across the internet helps them create a data set of relevancy, which is used to change the embeddings of the XLM-RoBERTA model to good search embeddings. The second thing that you need is a really solid pre-training objective. And the researchers introduced something called weakly supervised contrastive pre-training. It sounds very scary and very weird, but really all it means is that you're pushing together pairs that should be close together in vector space, and you're pushing away pairs of things that should be far away in vector space relative to their relevance and semantic meaning. So you might have a batch of training data that's sent over to the model during training that could include a query and a relevant passage, which is represented by the yellow text here, the yellow query and the yellow document. And then you might have in-batch negatives, which are just other randomly sampled passages that are not actually relevant to the query, which are represented by this other color here. You pass that to the model and you look at how the model is clustering the query and the correct passage versus the query and all other incorrect passages. And you want to push away, you want to train the model in such a manner so that it pushes away the incorrect passages in vector space and pushes the correct passage together in vector space. And that is allowing us to encode this relevance information that's important for search processes. The third and final contribution that the researchers make in order to make multilingual search work really well is not only do you start by having this model and then you train it in this fashion so it's kind of good at doing that task in general, is that you also need to use specific data sets that are designed for retrieval tasks in order for this model to get really good at doing those types of tasks. So on the bottom right is a table from the technical report that describes the different research papers that were used in the different data sets that were used in the fine-tuning process. And in my chart on the left, I took the liberty of kind of going into each of those data sets and figuring out what broader buckets they kind of fall into. So these data sets cover question answering, duplicate identification, multilingual retrieval. So you might have some question in one language, find it in the same language, or you'll have some question in one language, find it in a different language. Natural language inference, which is finding the relationship between two sentences, and just regular English retrieval. The researchers also use other more state-of-the-art techniques like finding the hard negatives for the points that you're interested in, knowledge distillation, and cross-encoding in order to really, really solidify the idea of having a good embedding model across languages. And that's awesome. Now we have a way of representing text across languages that is specifically tuned for multilingual semantic search. But we have another problem. We've embedded all of our data and we have tons and tons of vectors, but how do we actually search over those vectors efficiently to find the information that that's relevant for us? That's where Pinecone's vector database kind of comes in. What ends up happening when you have a bunch of vectors in vector space is that you'll have some user query, you'll want to embed it, and then you want to map that user query or measure that user query against all of the documents that exist in your vector database. And you want to find the documents that are closest together in vector space, which is going to be the highest probability of things that are relevant for your user. For example, if your user asks a question, you want the most relevant answer document to kind of pop up and be close together in vector space. Problem is that when you have tons and tons of chunks and tons of documents, this comparison that you have to do against every single document becomes very computationally expensive. And because it's like a database, you need a lot of management-y type things in order to make it work for your application. And that's what Pinecone kind of abstracts away. It helps you kind of index this information in a really efficient fashion so that you can find the closest vectors in vector space. And it turns out that once you turn a multilingual or multiple things in different languages into vectors, they're just vectors. So it doesn't matter to the vector database what language your content is in, as long as it's represented in the same vector space. This is where Pinecone Inference and Pinecone Serverless kind of come together to make it super easy for us to build this multilingual search application. We're able to use Pinecone Inference, which hosts the multilingual E5 large model inside the same SDK as the inference database, which means you can embed your data and upsert your data into your index without having to leave the Pinecone kind of universe, which is super nice to use the single API for both purposes. And our demo application is going to kind of show us how to do that. So here's some example of how you would use the Pinecone Inference offering in order to get embeddings for some text that you're passing in. You don't need to think about hosting the model. You don't need to think about tokenizing your data because the tokenizer is located with us. And you're kind of able to embed the data and upsert it within the same workflow. Then after you've embedded and upserted the data, you can query you can embed your query and kind of search over your index in order to find the most important data that you want to find back, which is pretty straightforward, not that many additional lines of code. Okay, enough of me kind of going on about all of these different concepts. I think it's time for us to actually build this application that I was talking about, where we apply a multilingual semantic search to Tatoeba to learn English and Spanish a little better. So this is what we're going to build in the demo. What we're going to do first is a bunch of data preprocessing and upsertion steps where we take all of the English and Spanish translation pairs from the Tatoeba dataset. We subsample them so that we can kind of get a way of working through the dataset. We split them, we embed them, and upload them to our vector database. So they'll exist together and we won't know what sentences are translations of the other. We do this just for instructive reasons, just to understand the capability of the vector database to search across languages, in addition to Pinecone Inference supporting those languages. Then we're going to demonstrate how to do monolingual search, where you have one sentence in one language and you search over it in the same language, and cross-lingual search, where you have one sentence in one language and you search over in the other language, and how you can use the same pipeline to support multilingual semantic search for this operation, which will be super interesting and important. So I'm going to take a moment to fire up my Jupyter notebook so that we can kind of see what is going on. So if everyone would give me just a moment to switch tabs here. All right, just a second. Let's see if that looks good on screen. All right, that looks fantastic. All right, this notebook is available in the Pinecone Pinecone examples learn section. I'll drop the link in the chat in just a moment, but you can access this notebook and just use it directly in Colab to follow along in the examples. So what we're going to do is first install our dependencies. We're going to install Pinecone and the Datasets library from Hugging Face, and we're also going to install Pinecone notebooks in order to kind of make it easier to do some of the connections that I was talking about prior. And I've went ahead and installed those already, so I'll just kind of scroll past this. We're going to use Pinecone inside Colab in order to activate and set our API key, which I've set already, and we'll download and install the Tatoeba dataset. I'm using Helsinki NLP's instantiation of the Tatoeba dataset. It's really big, and we're probably not going to be able to search across the whole dataset in a really nice, clean fashion. So instead of doing that, what we're going to do is subsample the dataset, so it's a little easier for us to work with. When we download the data, we can see that it comes in the form of ID and translations, and we have English pairs, for example, the sentence, "Let's try something," and Spanish pairs, which is going to say intentamos algo, which is pretty awesome. Great. Like I said, we probably won't be able to deal with the entire data set of like 200,000, 2 million plus pairs just for English and Spanish. So we're going to subsample the data. And the way we're going to do this is we're just going to look for all strings that have the word park in them in order to kind of show this instructive example of one word having multiple meanings and how you can use semantic search to kind of bridge the gap in those situations. So all we're doing is looking over all of the pairs on the English side, finding the sentences that have the word park in them, and subsampling the data so that we're left with about 416 translation pairs that kind of use this idea. And when we look at the first translation pair, we get this sentence: "When my brother was young, I often used to take him to the park," which is great. That's relevant for our purposes. We can explore the data a little bit just by walking over this stuff. And you can see that we are getting sentences that are not necessarily as relevant to the problem that I was describing. "Sir, you're not allowed to park your car here." That's not what we want to be thinking about. The next thing we're going to do is set up our index. This is super easy with Pinecone Serverless. We're going to create our index name, the dimension, which represents the size of the embeddings that the model is going to output. And we're going to check if the index already exists. And if it does, we're not going to override it. So we can go ahead and run that. Second thing we're going to do is embed our data. One thing I want everyone to kind of come away with is that when you use the multilingual E5 large model, you're going to represent queries and passages differently in your data set. So when you're uploading data to your index, in this case, we're uploading the sentences that exist in the data set into the index. We're going to upload them with the input type of passage because we are searching over that data in our vector database. The queries are going to be the strings that we're passing to the vector database that we're trying to find relevant stuff for. This asymmetry is important because you might have really long chunks of documents which might need to be encoded differently than the queries with respect to the model in order to represent the concepts that are existing inside those documents. So I have a function here that takes a list of sentences, embeds them, and returns the embeddings. So we're going to pull out the translation pairs separately, and we're going to embed them, and we'll get this embedding list object back, which has a property of data and values, which is going to be the actual embeddings. The next thing we're going to do is we're going to batch embed and upsert our data to the index. It's important to keep in mind that the batch size for our model is 96, so we can embed like 96 different things at the same time, and that we have to keep in mind that we can't pass in more than, I believe, 507 tokens for each of those embeddings. So that's something we'll have to be careful about. Because we're working with such a small corpus, we're just going to embed the data in batches directly without thinking about the rate limits. But if you were to scale up this problem, you would want to make sure that you're attending to the rate limits provided by us at Pinecone. So now what we've done is we've taken the text, we have a set of it, we have attached the language information about the text, which will be important for the querying later, and we've attached IDs to the text to make it easier for us to upsert. We're going to use the map functionality from the Datasets library to make it easier to kind of batch embed all of this sort of stuff. All we're doing is we're mapping over the set of data that I described prior. We're chunking it into batches, and we're passing it to our embedding and upsert pipeline in order to get it inside our vector database. That's what this function is going to do, and the handy dandy sentence mapping operation is going to make it super easy for us to embed those things at the same time. Like I said, if you are going to be doing this on your own and you're uploading more than like 10,000, 20,000 sentence pairs, you might want to think about implementing some sort of ability to look for rate limiting. And in our documentation, we do have ways of kind of handling this. Cool, so I'm going to let that run a little bit. We're almost done getting our embeddings created and upsorted into the index. Then we have the fun part, which is going to be actually querying that stuff in the vector database. So I'll go back and just take a quick look. All right, it looks like our map operation is done, and we can move on to the second part, and we can see that we get this embedding kind of out. Now we're going to do our embedding function for these sentences. So this is the idea that we are going to have queries, so things we're going to ask our vector database that are going to be represented differently using the input type of query, and then we're going to look for all the stuff in vector space that is close to that query in vector space, no matter what language it actually is in. Now, in order to kind of be a little more instructive about what is happening here, we're going to add a filter on our query operation to only look for the English sentences, and we're going to use an English sentence just to demonstrate that this pipeline that I've created allows you to do English semantic search. So I'm going to go ahead and hit enter, and we get these results back. We get a bunch of sentences that were kind of not direct translations of the sentence that we're looking with, which is what Tatoeba would give you, but sentences that are similar and relevant to what we might have to end up writing about. So I'm playing in the park. We were playing in the park. It was fun playing in the park. The kids playing in the park. They were playing baseball. There were a group of children playing in the park. These are not things that have a lot of overlap outside of the word playing in park in this text, and probably would not be surfaced if we just did keyword search. So that's cool. But what happens if we do Spanish to English search? So you can see in this block, all I'm doing is passing a sentence in Spanish, which is my poorly translated way of saying I played at the park at the end of the week. It doesn't even matter too much that the translation's not that great. Remember, we're just learning the language. We're going to filter on languages English, and it turns out that we get sentences that are relevant to that query, even though there is not keyword level overlap. We don't see Spanish words in this English text. We just see the English text that's coming back. Yet we're still getting sentences that are relevant to the sentence that's being passed. On Saturdays, we usually visit this park, which is relevant to going to the park at the end of the week. That's really cool. And the fact that we can do that without doing much else to the actual pipeline is a testament to the efficacy of this type of technology. Finally, we're going to do English to Spanish search, which is the thing that we wanted to enable in the first place. So if I go ahead and hit enter, we can now complete our assignment. We said I went to the park last weekend to play sports, and we're getting sentences about going to the park the last, I believe, Saturday or Sunday. And yesterday I went to the park, and some other questions and things that are kind of related to that. Again, there's no keyword overlap between these things, right? And there's no translation that's happening. We haven't told our vector database what sentences are translation pairs to the other. All we did was embed them in the same vector space and compare where they are existing relative to one another in vector space and returning the ordered results to that. Now, just to prove to you that this is actually what's happening, I'm going to send in a sentence that is not relevant to what we need, but has similar keywords. So these could be like the false positives or the incorrect things that should be passing in. and we're going to search over in Spanish. So I say, I need to find a place to park. And the first response that I get back is, where did you park? Something along those lines, and something about not finding a place to park your spaceship, right? These are things that are related to parking vehicles, whether they be in space or whether they be in real life. And that kind of shows us that we are encoding the topics and the concepts that we're interested in finding. So you could take this notebook, you could remove my filter that subsamples it and just scale it up to the entire data set and just see what happens when you do that. You could add in a bunch of other languages. The Tatoeba dataset has language translations across tons and tons of languages. You could just do all of them and just see what pops up. We're going to clean up our index and delete it here just to make sure we don't have that active anymore. And that will be our demo. I'm going to go ahead and stop sharing my screen and go back to the presentation. Alrighty. So we just built semantic search using the same exact pipeline, which was really cool. I want to leave you with some tips and tricks to think about when you're building your own multilingual semantic search applications. Remember to embed your queries and passages differently, especially when you're using Pinecone Inference. Don't forget about chunking your data. You'll still need to do that. The endpoint doesn't do it for you, and that there's a context window about 507 tokens. Whenever you're doing anything in a cross-lingual fashion, you should create an internal gold standard evaluation set for understanding how well that performance is across languages. It's very, researchers can't possibly test every single cross-lingual language that exists in the world. That would combinatorially, that would be way too many things to test at the same time. So if there's a specific cross-lingual use case that you want to use this model for, you should have a gold validation set of query and the relevant responses that should be pulled up in the top K or whatever, in whatever search you're doing in order to get that back. Take advantage of batching in order to embed lots of things at the same time in order to kind of support the rate limiting. And remember that you can use the same pipeline across languages. You don't have to do cross-lingual search. You could just support semantic search in the language with the same languages being the query and the documents. And the fact that you can use the same pipeline across those things is pretty neat. The last thing I would add is that you don't need to see semantic search as a replacement for full text search. You can use both kinds of search in the same pipeline in order to help users find the things that not only overlap with the words that they're interested in, but also are semantically relevant and similar to the things that they'd like to work on. All right, everybody, that's my presentation. I really hope that you were able to take away something interesting and important from this talk on multilingual semantic search. I did my best to cover a lot of the concepts that you might need in order to understand them. The good thing is that when you work with Pinecone Serverless and Pinecone Inference, you don't need to know too much about how these models are working or what they're doing under the hood. You can just use the endpoints in order to build your semantic search applications. Personally, I would love to see what everybody is working on, what you're building, or what you're thinking about building. So drop that in the chat, and I'd love to hear about what types of things you're going to be doing. This is the end of my presentation, and so we're going to open the floor to Q&A. I'll go down the Q&A and just see what people have in mind or what they'd like to ask about. If there's something that hasn't been addressed, or if there's something you'd like me to go over in a little more detail, I can try to do that during this time as well. Thanks, everybody, and let's jump in. Cool. It looks like Srinivas has said that there is a fashion item recommender that includes Pinecone embedding search as well as keyword search. So that's a great example of kind of using both of those properties in order to kind of get the thing that we're interested in. Jing Hao said, how do we evaluate semantic search results? This is a great question. This is very specific to the industry that you're coming from or working with. Generally, what people do is that they'll have a gold standard data set of queries that are coming in, and you'll have a gold standard of the documents that should be retrieved relative to that query. This is not a trivial data set to collect. So very often what people might do is implement something, see whether people are finding the relevant thing. If they are, also use that as a relevant way of kind of looking and finding this information. I highly suggest thinking about the type of industry that you're coming from, the types of queries that you're going to be asking, and the types of responses that you're going to expect to get, and use that to construct a gold standard data set to evaluate different types of search offerings. Srinivas is asking another question about language theory in general. So if it's possible to embed all these languages in the same vector space, does that mean, or sorry, I misunderstood, but if there's no actual language family, can that still be turned into a vector embedding? Yes, that is correct, because the way that these embedding models work, they don't care about the language that you're actually passing in. So theoretically, you could use multiple languages in the same sentence and it'll get embedded in some sort of vector space. Will that work as well as if you're using one language inside that search? maybe not. But that's something you can test for sure. And since English is a thing that people actually use, it might exist already on the internet. So it might have been scraped to create these embeddings. So it might actually exist. Srinivas has a bunch of questions, so thank you for your enthusiasm here. So how are we deciding what words to discard and what words to keep? When tokenization happens for the corpus, there is an optimization algorithm that kind of decides what are the most frequent co-occurring, like bigrams or trigrams or combinations of words or concepts, and you kind of turn the ones that are most frequently occurring into the tokens in the vocabulary, so you can kind of reuse that token over and over and over again. This is a little out of scope of kind of what we want to cover. So if you're really interested in tokenization, we have some articles on our website, but there's also a lot of good content about sentence piece and how it works on the internet. So keep an eye out for that. Srinivas, another question here about having tons of different languages. If there's a new language that isn't actually existing in the 88 languages, could that actually work? And what's the approach to kind of support that? This is a great question. If I remember correctly, there is a textbook from Hugging Face that they released a few years ago on transformers. And I believe one of the problems that they go over in the textbook is out of domain multilingual named entity recognition. So this is the same idea of like, okay, you don't actually have this language in the corpus, or you don't teach this model to work in this language, but how far can you get by training on a related language family and kind of going from there? So I would argue that, like, hypothetically, there's probably some merit here to language families and whether you can do enough to kind of get close to that language in order to do something that's helpful for there. And an example of this happening in the real world is that there are lots of languages in India, like there's Hindi, and I'm Gujarati, so there are Gujarati languages, and Gujarati has not as much content on the internet as Hindi does. So how would you build a large language model for Gujarati specifically? Well, you might have to include some Hindi data in order to kind of take advantage of that language distribution. Okay, Terry, great question. So what is the benefit of doing this over translating directly? So I actually have a slide for you that kind of helps answer this question. So why not do translation? So first of all, translation is actually really expensive. You can either do it automatically, in which case you will still have to verify if the translated vocabulary is correct, or you have to pay somebody to do it, in which case it can get very expensive. And then you have to think about all of the ways that the translation is going to be supported for. And you have to support that over time, right? So if you update your documentation, you have to retranslate it and make sure the retranslation is actually accurate. Now, full text search is great. Like, you can do keyword search with that. You can support and create those keywords for the specific languages, the customers that you're looking for, and help them kind of do that. But if you're actually trying to leverage semantic search, so if you're actually trying to help people type in queries and you're trying to find stuff that might not be as relevant to the query that you're passing in, but might not have keyword overlap at all, but it's still relevant, you're not going to be able to do that using translation whatsoever, because you're still using keyword search under the hood. That's where multilingual semantic search really allows you to kind of survive. So that's the use case. And I encourage you to kind of look into how much it would cost to translate and verify your stuff. It gets very scary really quickly. So doing something like this is a good addition. It might not be a replacement for having translation, especially if you're a really, really large website, but it definitely allows you to incorporate semantic search, which is not going to be something you get from translation. Steven has a question about being new to vector databases. What's the best practice for indexing, how to create it, how to upload? Some people saying saving the data in JSON format is good. What do I think? So there are a lot of different ways of embedding and upserting data using Pinecone. There isn't really like there are some documentation on our website on how you can efficiently index and upsert data. I've shown some examples of how to embed data and then upsert, and how you can kind of respect rate limits in order to do that really nicely. So it really just depends on the type of data that you're working with. I would try to do it programmatically so that you can respect rate limits. We have some scripts on our website that let you do this programmatically so that you can just like copy paste the scripts, point it at the data that you have located, and just do that upsertion and embedding. Vasileios, I hope I'm pronouncing that correctly. You have a question about training your own multilingual embedding model for a specific domain or extending one. Yes, you could totally do that. This is not something that Pinecone offers right now, but the idea is that if you're doing so good at generalizing across languages, then maybe you're still going to be pretty good at the in-domain stuff. But your point is great, right? Like if you're working on a domain or a vocabulary that has a lot of specific words that might not be tokenized the same as the words that exist across the internet, or if they're specific languages, then yeah, you could fine tune a model to do the same type of learning objective like I described before, like masked language learning or whatever, in order to have a better representation of the thing that you're doing. And that is generally the recommendation if your domain is extremely hyper-specific. So yeah, it's possible. Or you can just see how well stock embedding models work. That's where I would start. See how well the embedding models are working. think about how much lift you want and then try to train toward that. Jinghao has another question. If you ask some negative questions, like give me some healthcare companies other than the health field, the model's performance isn't very good, so how can you improve this? So lots of different ways to kind of go about this. This is a classic kind of issue that's difficult to handle with semantic search. You could have a layer in between the query and the vector database that transforms the user query into a lot of different other queries that are no longer negatives. Search over those queries, rank those, and return them back to the user. So you're basically, you might ask another LLM like, hey, take this input query from a user that has a negative in it or is phrased as if it has a negative question, convert it into a bunch of positive questions, and then just search for results for those positive questions. That's one way of doing it off the top of my head, but there isn't like a nice stock way of doing this just with the vector database. That's more of a data engineering / going to production type of problem. Will. This is the stuff I love answering, right? This is like the theoretical, like what is actually happening with these LLMs? Like what is kind of going on? So is language kind of interfacing with this thinking, or how does Pinecone kind of account for these cultural nuances? So it is important to keep in mind that the limits for the model and the limits for different languages and nuances are going to be restricted to the model. We're just hosting the model because we find it really useful for people to do, but we haven't like augmented the model further in order to make it have a much wider token window, for example. We're planning to expand the amount of models that we're hosting, and the other models that we might host might have larger token windows, which might be able to, context windows, which might be able to handle those use cases. In addition, how do we handle cultural nuances? For example, the wedding in an Indian context might be really different than the concept of a wedding in a Western context. So how can you account for that in search? That's a great question. That's something that you need to kind of benchmark and kind of see if for your domain, are you actually getting the relevant things, or do you need to apply something else like a multilingual re-ranker, which is something that Pinecone offers as well, in order to kind of get the more relevant cultural results. Or maybe you need to augment the user's input query in order to add additional context or information to get the things that you're kind of interested in. Anuj, great question. We've answered this kind of earlier. Theoretically, it should support things like English and Spanish because the embedding model doesn't care what languages are being passed in because it's been trained on all these things. But if your use case involves English or Spanish, you should have a gold standard data set just to make sure that it is doing what it says on the tin, right? I'd love for you to believe me like all as you want, but it's always important to have your own evaluation stuff in-house to understand what's going to happen. Next question from Srinivas. Thank you so much. This is a great comment for me. I'm glad you enjoyed it. If anyone has any more questions, please drop them in the chat. I would love to understand them and help you kind of figure things out. We have 10 more minutes. I'm here. Please use me as a resource. Tell me about things that you're building, especially related to multilingual search, and I'd love to help you kind of figure out how to go about all these sorts of things. So Menelos is asking what happens when the embedding model is used for a data set that is a low resource language. So this is the term of art that people use when we talk about languages that don't have as much data. And this is the idea that you might have a language that exists on this side of the distribution where you have like way less data, or you might not even like show up on the graph relative to like English or whatever. So the idea is that because you're training across languages in an unsupervised fashion, you're not telling the model what language it's working on. You might be able to pick up information across language families in order to help your model learn about something. So let me give you an example related to the one I used prior. So Hindi is a really big language in India, and so is English. So there are a lot of Hindi speakers and a lot of English speakers. I speak Gujarati, which is a language that's relegated to a specific state in India. So there aren't many speakers of Gujarati outside of India, outside of the state that the language comes from in India. So there's going to be less language data of that language in the world compared to the language of Hindi and English. But Gujarati and Hindi are mutually intelligible. So I can understand when someone speaks Hindi to me, and if someone only speaks Hindi and I speak Gujarati back, they can understand some of the words that I'm using. So there is a language family that kind of exists that kind of branches those two languages. So if I wanted to build a large language model that could help me learn more Gujarati, for example, I would probably need to take advantage of the fact that there's a lot of Hindi text out there and a lot of other Indian languages out there that I could use as training data in addition to the Gujarati subset that I have to kind of learn that additional information. So that's what you would need to do. So theoretically, like it would still be fine, even though that data does not exist only for Greek. Like the motivation here is not to build a large language model for specific languages all the time. You want to build something that kind of learns relationships across languages, which lets you leverage that type of information. Igor, great question. If we use a big popular model like OpenAI's Text Embedding 3, will we have better results? Really depends on the task that you're working with, really depends on the thing that you're trying to do. Multilingual E5 large is designed for multilingual tasks. So it's going and retrieval tasks. So it's going to be really, really good at doing that. OpenAI Text Embedding 3 is kind of trying to do a bunch of different things. Like it's trying to be really good at letting you do classification. It might be really good at letting you do some sort of multilingual things, but you might not know. The advantage of using an open source model like Multilingual E5 large is at least you can look at the researchers' research papers and really try to understand what exactly is happening under the hood. But look, if it ain't broke, don't fix it. Like if you're using OpenAI Text Embedding 3 and it works really well, and it's good for your use cases, you can still use that with Pinecone. You can still embed your stuff and just upload it into your vector database and not have to worry about it too much. So that's theoretically, you will benefit if you're doing specifically monolingual or multilingual semantic search and you want to scale across that, you will benefit from using a model like this, but you should have your gold standard data set and kind of go from there. Jinghao has a good question. If the data in Pinecone needs to be constantly updated, is there any lower cost approach? I know that our serverless offering allows you to decrease the costs that you have relative to using pods, so you don't have to keep something up all the time and kind of doing that sort of stuff, but I'm not sure if there's a clear way to getting around the updates. I'm happy to refer you to any of our solutions engineers if you have any questions specifically on your use case, so feel free to reach out to me or to Gibbs to kind of help you get started with that. It looks like we're nearing the end of a lot of the questions that are kind of coming in. We have a few more minutes, so if anyone has any other burning questions they'd like to throw in, I'm happy to kind of help you learn about how to think about these sort of things. One thing I will do is stop sharing my screen and throw in the example into the chat so that everyone can kind of take away that for users. So let me go ahead and give you the link to the example page, which I will drop into the chat. Here you go. This is the specific example. And if you want to read my article about this concept, you can look at this article on Pinecone, which should help you learn about these sort of things. All right. I think that's pretty much everyone's questions. If anybody has anything else that they're interested in learning about, please feel free to contact me at arjun@pinecone.io, which I will drop in the chat here, or on LinkedIn. I'm happy to help you think about these problems, or at least get you in touch with the people that should help you figure them out. Gibbs, what say you?
Yeah, thanks, Arjun. It looks like we might actually still have 2 questions left in the Q&A.
Sorry, I missed those. Let's see. Rahul, you're asking about querying the correct table when you have a text to SQL model and when you have multiple table columns and names. I'm not quite sure how you can go about building the text to SQL model without any more context. So feel free to email me for a follow-up there. I can kind of help you think about that. Srinivas has a fun question. What happens if you ask in a Martian language? I'm not really sure, but that is something you can test with the endpoint. You can try to grab the notebook, type in something and what you think a Martian language would be and see what happens. That would be really fun and exciting. Or you can find a constructed language, like something that that people have kind of made, and see if that actually ends up working. Thank you. This is my fun little collection that I really enjoy. All right, I think that's everything.
Yeah, thanks so much. Yeah, and we will follow up with everyone that attended today with the recording and the resources to the notebook and the blog that Arjun wrote via email shortly after the session. But yeah, thanks again for everyone joining.
Thanks, everybody, and feel free to reach out.